Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 7, OSPF network types, issues, and comparisons. So we've got quite a bit of different material to look at here before we move on to multi-area OSPF. We're going to be taking the network from the last video, which we will recap here, and take a look at the different default OSPF network types and what to look out for when you're configuring these. That part usually goes smoothly, but occasionally you've got an adjacency issue, and you need to know why that happens between different network types. After that, we're going to take a quick look at detecting OSPF network issues with an important debug command. We're going to see how OSPF comes up with a cost for a path, because OSPF assigns a cost to every interface. We need to know some default settings for that, and we need to know how OSPF comes up with that in the first place. I'll also show you how to change it, although you'll find with OSPF you don't have to do that very often, if at all. Finally, we'll do a quick comparison of OSPF to RIP, just reminding you of the differences between the two, not just for the exam, but for the real world as well, because sometimes RIP version 2, especially over RIP version 1, works perfectly fine. There are local area networks all over the world right now running RIP version 2, and they function fine. So we'll take a look between those two protocols and compare the two. Revisiting our previous network, our previous videos network, we finished up with this, and just to review, routers 1, 2, and 3 are connected over a frame network in area 0 with R1, the hub, acting as the DR. Of course, there is no BDR. All three of those routers are advertising their loopbacks into OSPF as well. Routers 3 and 4 are connected via an Ethernet segment. They're in area 34. And finally, R4 has its loopback advertised as well, but in area 4, which necessitated us building a virtual link using area 34 as a transit area, which gave area 4 a logical connection to area 0. So as we look at these OSPF network types, we're going to take a look at how each one of them defaulted to a certain network type. And I've also got here on the board some details that you need to be aware of. We're going to go down. These are 5 really of the 7 OSPF network types. These are by far the most common, especially the top 3. And you will have some more specialized types that you'll need to know about should you choose to pursue your CCIE in routing and switching. But for right now, this is what we need to know, and we're going to take a look. I'll keep bringing the router screen up, and we'll take a look at each one of these types. The first one is broadcast, and we have a broadcast network segment between routers 3 and 4, and there is a DR-BDR election, and there's no requirement on which router should be the DR or the BDR. In our particular configuration, we really didn't care. That's a long command, but you get a lot of really good information out of it. Show IP OSPF interface, and then follow that with the interface name and number. And here you see it did default to the network type of broadcast. This is the DR. There is a BDR. We know that's router 4 because that's the only other router on the segment, but we also know that because that's router 4's RID. Note the hello and dead times. These are the defaults for a broadcast network, and these are what actually have to match in order to have an adjacency form. It's not really the network type. It's not really the network type. Let's take a look right now at router 4. Same command. That's the shorter version of it. We're always looking to type less, right? The network type is broadcast. The cost of this particular interface is 10. This is the BDR. Here's the RID of the DR, which we know is router 3. So everything looks good right there. But let's change the hello timer. We did that in the previous video. We're going to do it here as well. I'm going to change it to 5 seconds. That's the interval between hellos right now. Let's take a look at our adjacencies. It's still full. Let's see if it stays that way. Because we got to wait for the dead time to tick down. We're not going to lose the adjacency immediately in this particular example. But you'll notice that it keeps on ticking down. It doesn't look good. We got about 12 seconds to go. And of course, this is the kind of thing that happens before we get called somewhere, right? We walk in and the adjacency's down, and we got to be able to tell why it went down without knowing what actually happened. Because, you know, everybody always says it was like that when I got here. Well, we run show IP OSPF neighbor right now, and we have no neighbors. And we didn't change the network type. The network types still match, but the hello and dead timers do not. That's what we have to be able to find. Your number one debug for diagnosing problems with OSPF is debug IP OSPF ADJ for adjacency. We're going to hit enter, get a message that it's on, and we're just going to wait. We're going to see what we get here. And we already see the problem. I'm going to run undebug all, which turns off all debugs. If I just wanted to turn that one debug off, I could have typed in no debug IP OSPF ADJ. We see immediately, here's the problem. Mismatched hello parameters. Once you see what the problem is, it's not that hard, but you got to know how to find it. And that's the problem right there. It's not the network type. So we're gonna turn that debug back on. And we're going to go back to the interface. No IP OSPF hello 5. And I think pretty shortly, I'm going to go ahead and save here. Pretty shortly we're going to start seeing an election and all kinds of things going on. I could have just typed in IP OSPF hello 10. But I like to negate the command and get it out of there. And there we go. We're off to the races. We just had the DR election up here in the middle. I will stop the debug here in a second so we can take a look at a little of that. As we go back up to the top, you can see where it went into initial state here in the middle. Then it went to two-way. There's initial. Then to two-way communication. Then a DR BDR election. Went through exchange state. Synchronization is full. And then finally, we have our adjacency back. Now it's important to note, you need to know what a broadcast network is, and an Ethernet interface is always going to default to broadcast. But you need to know why that adjacency went down. It's actually the timers that are the problem. Those have to match. So now we've got an NBMA network, non-broadcast multi-access. This is what a serial interface on a frame relay network is going to default to. On routers 1, 2, and 3 right now, they're all running NBMA on those serial interfaces. There is a DR-BDR election. We rigged it so there would be no BDR. The hub should always be the DR. There should be no BDR. The hello timers are different, though. On NBMA, the hello timers are 30 and the dead timers is set to 120. So let's go to router 1 and take a look at that. It's a lot to type, but it's worth it. You can see here on router 1 serial 0 interface, it defaulted to non-broadcast. And you can also see this one is the DR. You can also see that the hello and dead timers are different from broadcast. This is a great command too, because you can also see who your neighbors are and who you have your adjacencies with. Great command. Show IP OSPF interface followed by the interface name. So that's an NBMA in a nutshell. Now we're going to look at a point-to-point connection. And what we're going to do here is build a point-to-point connection between router 1 and router 3, because these two routers are also directly connected at their serial 1 interfaces. So that's what we're about to configure. And that's the 172.12.13.0/24 network. We'll put it in area 0. And we already have an adjacency up. The top one, you see now we've got two adjacencies to router 1. One's going through the frame and one is not. One's going through serial 1, which is the directly connected interface. The highlighted one is the one we're interested in right now. Notice that there's a dash after full. Now what we've been seeing there is DR, BDR, or DR other, but this time we see nothing. It's kind of odd. Let's go to router 1 and see what we see. Same thing. We're still seeing these two attempts from the previous video, and as I told you then, those will take a long time to go away after you change the OSPF RID. So don't worry about that. Again, though, we've got this dash here. The dash indicates that the other router, in this case router 3, is not a DR, a BDR, or a DR other, because there is no BDR or DR election on a point-to-point network. Very important concept here. There's no DR, BDR election because by virtue, I mean, what is a point-to-point link? How many endpoints does it have? It's only got 2. That's what a point, otherwise it's not point-to-point. If there are only 2 endpoints, there's no reason to elect a designated router to flood changes to other routers in that segment, because there's only one other router on that segment. So there's no DR, BDR election on a point-to-point link. If you see that dash there, it's perfectly normal. That's what we expect to see. Note that the hello and dead timers are both 10 and 40. Now you've also got point-to-multipoint. That can be configured over frame relay as well. It's not the default, and it's kind of specialized. Most of the time you're going to see it just kept at NBMA. What you need to know about that for now is that OSPF sees this network type as a collection of point-to-point links. So there is no DR, BDR election on a point-to-point, point-to-multipoint network either. But keep in mind that the hello and dead timers are different. 30 and 120 as opposed to 10 and 40 for point-to-point. And finally, for virtual link, we're going to bring a virtual link up that we built in the last video. And you remember the command to see that is show IP OSPF virtual link, or just vir, that should do it. Yep. This defaults to a state of point-to-point. And you'll see right there that it does have the same hello and dead timers as a point-to-point network type. But you're not going to see it under the neighbors. You're not going to see a virtual link neighbor of any kind. But a virtual link is technically an OSPF network type. So those are the 4 types you need to know for the real world and for the exam. You need to know which ones elect DRs and BDRs, which ones don't, and I would know those timers cold. And please keep in mind that it's actually the timers that cause the trouble with OSPF adjacencies as opposed to the network type. One other command that's really handy for detecting an OSPF network problem is not a debug command, it's a common show command, you tend to see this one not run as often simply because the output is so huge. And that's simply show IP OSPF. And believe it or not, after all the typing we've done for some of the commands, that's it. But show IP OSPF does give you quite a bit of information. It does show you your local RID, that kind of thing. Whether or not it's an area border router or an autonomous system border router, if those terms are a little fuzzy to you from your CCNA studies, we're going to go over those in depth in the, one of the multi-area OSPF videos. But what you want to look out for here, I mean, there's a lot of information here as far as the number of external LSAs. You may not use that for a while, but what you want to watch out for down here where you've got area backbone and then area 34, a number to keep an eye on is the SPF algorithm executed how many times. If this number continually increments, it's a good sign you've got a flapping link in your network somewhere. Something just keeps changing and then changing right back, because that number should be fairly steady. Now, it's not going to stay the same, because remember, every 30 minutes the updates are going to go out, and the algorithm will be run at that time. It's going to be run anytime the router receives an LSA that reflects a change in the network topology. So you don't want to look for that number to be static, but you do want it to be not incrementing every 30 seconds or every 60 seconds. If it is, then there is a problem somewhere. Moving on here, let's take a look at how OSPF comes up with the cost. And I say path cost determination here. What we're really looking at is how it comes up with the value it gives an interface. Bringing the table back up, let's look at an OSPF routing table. And here, of course, you see we've got some load sharing going on right now, actually, between 3 and 1, since we've got 2 paths now. And here's one set of brackets we can look at. The first number in that set of brackets is the administrative distance of OSPF. That's 110. 65 is the cost to get to that particular destination from here. And how that cost is arrived at is that each port along the way is assigned a cost by OSPF. And you can see what a given interface's cost is with the show IP OSPF interface command. And at the very end here, as we've seen a couple of times already in our OSPF discussion, the cost for that particular interface will be right there at the end of the command. Now, how does it come up with that to begin with? There's a formula that Cisco would like you to know about, an excellent idea to know about this before you take the BSCI exam. The OSPF port cost calculation formula is 100 million divided by the interface bandwidth in bits per second, not kilobits per second, not megabits per second, not gigabits per second, bits per second. Very important detail. I put on this board for you 5 common default values for interfaces. 56K lines connected to a 56K line. Their cost is $17.85. A T1 line, as we just saw, a serial interface. OSPF does the same thing that EIGRP and IGRP do. OSPF assumes that serial interface is connected to a T1 line, so the cost came out to 64. Ethernet cost is 10 by default, regular Ethernet port. If you're still running token ring, a 16 meg token ring cost is 6. And for both 50 and 100 meg Ethernet, the cost is 1. There may occasionally be a time where you want to change this. And what you can do, it's actually done with the bandwidth command, just like you did with EIGRP and with IGRP. What we could do in our particular network here is tell OSPF, hey, that direct serial connection between R1 and R3, that's really running at 512 kilobits per second. It's not running at T1 speed. So what we would do in this scenario is go into router 3 and router 1, and on the serial interfaces, use the bandwidth command, just like we did with IGRP and EIGRP. That gives the routing protocol a more accurate picture of what's actually going on. So if we change that on both sides, we don't have to clear anything, remember, because OSPF is going to take care of that for us. You'll notice now already we've only got one path back to the loopback on router 1, and it's via the frame cloud. That's because the cost is still 65. But when we changed the bandwidth setting on serial 1, notice the cost went right up. We cut the bandwidth setting from 1544 to 512, which is cutting it by about 2/3, and then the cost tripled and went from 64 to 195. So that's how the cost gets changed, is we actually change the bandwidth setting on it. Because if you keep that formula in mind, you'll know that change the bandwidth if you need to do that. I'm not going to tell you point blank, outside of exams, it's very rare that you have a real need to cut an OSPF cost. Although it does come in handy with a situation like we saw on our network. Let's say that frame is a T1 line and the direct connection or another type of connection between the two using the serial interfaces is a 56K connection or is a slower connection. Then it's a good idea to tell OSPF, hey, here's what the real speed is. Don't assume that it's a T1 line. There's also one other command that I'd like to show you. We can change the value that OSPF uses to base its path calculation on, that 100 million. You better have a really good reason to do that outside of passing the exam. Cisco's kind of big on you knowing this command for the BSCI exam and a couple of their other exams. And it is auto cost reference bandwidth. Rolls right off the tongue, doesn't it? This is the command to change that value that OSPF is using to calculate bandwidth. I'm not saying you'd never use this, I'm just saying it's a very specialized command. And please note that even though the calculation that I showed you uses bits per second, this command uses megabits per second. Always be really careful with Cisco and always use iOS help when you're about to enter a value that has anything to do with speed. Because some of the commands are going to reference bits per second, some of them are going to reference kilobits per second. This one references megabits per second. So I don't care how well you think you know a command, always use iOS help and just take a look at it. I didn't do that with the bandwidth command earlier because I have done that about 10,000 times. Just keep using iOS help and check those values. When you're doing quality of service later in your studies and you're changing numbers around, use iOS help and make sure you see what value it's using in the first place. Because if you're thinking kilobits and the router's thinking megabits, you are not going to get the result that you wanted. Now this seems like an unfair fight, doesn't it? OSPF versus RIP. OSPF's got all these great features. RIP really doesn't have many. But we're going to do a quick review here of the major differences between the two. And OSPF does have one major drawback that we're going to address at the end of this comparison. And then as we look at multi-area OSPF, we'll see how we start taking that into account. But right off the bat with OSPF, OSPF's metric is far superior to RIP. Because as you remember, RIP's sole metric is hop count. It doesn't know if the hop is a 26K line or a T1 line. It's just a hop to RIP. Where OSPF has cost, and while we can adjust it most of the time, the default settings do a fine job. So that's the first one right there. And that's because OSPF uses a composite metric, where RIP does not. I'm going to put that right up there. OSPF does not have a maximum metric. It does not have a metric where it says this network is unreachable, where RIP does. RIP has a maximum hop count, as you recall, of 15 to combat the counting to infinity issue that comes up with distance vector protocols. OSPF doesn't have to worry about counting to infinity because it doesn't have a hop count to begin with. OSPF is going to eliminate almost all routing loops by itself. Now we've got VLSM support. OSPF does support VLSM. RIP version 1, as you recall, does not. And RIP version 2 does. It's another good difference for us. OSPF uses your network bandwidth much more efficiently than RIP does. Why? I knew that was right. Much more efficiently than RIP does, because RIP is sending out those updates every 30 seconds. No matter what, it is sending it out and sending it out and sending it out. And then finally, OSPF does have the every 30-minute LSA flooding, but still, that's every 30 minutes as compared to a full routing table every 30 seconds. So that's not much of a comparison. Now, OSPF is going to multicast those LSAs again only when on the initial adjacency, a network change, or the expiration of that 30-minute period where there haven't been any network changes. RIP version 1 broadcasts and RIP version 2 multicasts, but they're still both sending out every single route they know. And this is something you might not know about RIP. RIP updates can only contain up to 25 routes. So if you try to run RIP over a WAN and you've got 200 routes you've got to let all the other routers know, it would actually take 8 routing update packets. That's a really important detail. Even if you've only got 35 routes in a WAN, not only is RIP going to broadcast or multicast updates every 30 seconds, it's got to send 2 different packets. That's a lot of bandwidth. That's a lot of bandwidth. As we mentioned, and as you've seen, OSPF converges much more quickly than RIP does. You can be working on a RIP lab in your home lab and have 3 routers and have a problem or change something, and it could take some of your routers 20 minutes to catch up to the changes you've made. Not all the time, but it does happen if you remove a route. Boy, I mean, it could take a while for that route to finally come out of the table. If you take a route out of an OSPF network, every other router knows about it in seconds, or less than a second. It's that fast. And then finally, OSPF allows us to create a hierarchical scheme. And RIP does not. Well, that sounds real pretty and it looks real good. What the heck does that mean? It means that through the use of multiple areas, we can create a layered network. Because as you're going to see in the multi-area OSPF videos, you don't always want every router to have a full routing table, especially if it's always going to have the same next hop IP address no matter what. RIP doesn't allow us to do that. RIP is just one big flat network. There's nothing we can do about it. Now, all this sounds great, but everything has a cost. Everything that we do on a Cisco router has a cost. And what you'll find is that the one drawback of OSPF, especially when compared to RIP, is that OSPF is a lot harder on your router resources, your memory and your CPU than RIP. That's the big drawback. That's where you've got to watch things. Because RIP, I mean, when you get an update, you unpack it, you put the routes in the table, that's it. OSPF, you got to run the algorithm against the database. You got to keep the database to begin with. So that's something to keep in mind, is that OSPF is basically harder on your routers than RIP is. But if at all possible, we really do want to run OSPF over RIP.